go back to the first day. Here we are, we got an altimeter setting of 30 inches and the altimeter saying 21 feet. We're going to take off on a cross country and we're going to fly over to Boston, where it's also 21 feet elevation. Now as we come into Boston, we're kind of busy because it's our first time into Boston Logan Airport. And we're coming in at night, so we're very busy trying to figure out where the airport is and look for it. They tell us that the altimeter setting is 29.9. Except we're so busy that we fail to reset the altimeter as we should to the current altimeter setting. We fail to do that. We should, but we fail to. So we are coming in and our altimeter is set to 30 inches, as it was at New York. But we didn't set it to 29.9. Now you know there's going to be an error of 100 feet. We just talked about that. Now, my question to you is this, class. We're going to be off by 100 feet. Is this an error on the side of danger, or is this an error on the side of safety? Danger? Danger? Safety. Safety. Anybody else got an idea?
Depends on how you're 100 feet high.
What? You're 100 feet high? So that's an error on the side of safety, you're saying, right? Huh? Well, I'll tell you.
You're going to be lower than you.
You're going to be lower than you think you are. This is an error on the side of danger. You're not 100 feet high. You're 100 feet low. Because look what happens. You know when you land, your altimeter is going to read 121, isn't it? But when your instructor, what did he tell you about those night landings? He said, when you turn final, check your altimeter. Be sure you're at least 200-300 feet, or at least 100 feet when you're on final getting in close, didn't he? So you check your altimeter says 121. Would you say, oh, I got it made, I'm 100 feet in the air? Where are you really? You're already on the ground, aren't you? You're lower than you think you are. Now there's a lot of confusion. A lot of people mix it. Even with experienced pilots, if you asked them this, they'd get a little confused for a minute about this. So we have little guaranteed methods. And there's a little rhyme that works here also. I want you to remember this forever. This rhyme says, if you fly from a high to a low, look out below. Okay? If you fly from a high to a low, look out below. And that's exactly what we're doing here. We're flying from a high pressure area to a low pressure area. And we failed to reset our altimeter, so look out below. Okay, you're going to be lower than you think you are. Okay? Now, of course, if you fly from a high to a low and you do set your altimeter, then you don't need to worry about being lower than you think. You'll be right on. Okay. Any questions on that? Okay, now, let me tell you this, class. I'd like to tell you, we're going to talk about colder than standard temperatures. We're going to talk about colder than standard temperatures right now. But I want to tell you this before we start talking about this. I want to tell you, class, no matter how cold it is, I don't care if it's 26 below zero, and you're given an altimeter setting of 30 inches, when you land at that airport, your altimeter will read field elevation. There is no error, no matter how cold it is, as long as you set your altimeter to the altimeter setting before you land at that airport. All right. But there is an error because of cold air. Take a look up here. Here's an obstruction that's 4,000 feet. Now, I don't care whether it's a hot day or a cold day, that thing's always 4,000 feet. Now, on a cold day, the air is more vertically compact. On a warm day, the air is less vertically compact. Now, what do I mean by a cold day and a warm day? I mean colder than a standard day. On a cold day, the air is more vertically compact, so that when you fly to 4,000 feet on your altimeter, you're actually a little bit lower than 4,000 feet. But it's not really a hazard to other aircraft, because if you think you're 1,000 feet from other airplane, you're all a little closer to each other, but not that much of a hazard. And on a cold day, it's not a problem, because when you come into land, your altimeter will read the elevation of the field, because you see, on a cold day, the air is more vertically compact. You're a percentage lower to the ground than you think. Well, let me show you something here. Let's say we're going into an airport here. Let's suppose that this airport is, 5,000 feet above sea level. Okay. And here we are on final. Here we are at 6,000 feet on our altimeter. Here we are at 5,500 feet on our altimeter. Here we are at 5,200 feet on our altimeter. Now, I want to tell you this. There is no way on a cold day of really knowing exactly how much lower you are than you think you are. Because you would have to go out and sample the air all the way from the ground up to whatever your altitude is. There might be times when the air is a little colder for a few hundred feet and then a little warmer for a few hundred feet. You can't really compute your true altitude above the ground without a radio altimeter of some kind. But we do know if the air is cold, it is more vertically compact. And I want to tell you something just for you to remember. On about the coldest day, you might be about 10% lower than you think you are. About 10% is a nice number on the coldest day. So that means if you think you're at 6,000 feet on your altimeter, that means you really think you're 1,000 feet above the ground. You're actually going to be 100 feet lower than you think you are, right here. When you're at 5,500 feet on your altimeter class, how much lower to the ground are you than you think? How much air do we have here at 5,500 on our altimeter?
550.
50 feet of air. You see, we think, here we thought we were 1,000 feet above the ground. Here we thought we were 500 feet above the ground, but we really were 50 feet less than that. Here we thought we were 200 feet above the ground, but how much lower are we than we think? Sure, we're only 20 feet lower than we think. So you see, this is the important thing to understand here. And I can tell you this, if you went over to some airport and started talking to some private pilots, you wouldn't run into many that really understood this concept of colder than standard air. You see, you are a percentage lower than you think you are, but you are correct whenever you land at your destination. Whenever you land here and you have the current altimeter setting correct, we have no error. The quantity of error decreases to 0 whenever you land. So, is this a danger to us? Well, it can be. When would it be a danger to us? It would be a danger to us whenever we think we're going to clear an antenna that's 3,000 feet above the surface. Or how about this? Flying in mountains in these conditions. Let me dim the lights here so we can see this shot a little bit better. What we have here is we have a mountain that's 15,000 feet above sea level right here. And we have Denver, which is 5,000 feet above sea level right here. Now, you're flying at 16,000 feet on your altimeter, planning on flying across these mountains at night. You think that you're going to clear these mountains by 1,000 feet. But if it's a real cold day, and even with a Denver altimeter setting, you might be 10% lower than you think you are. 10% of 11,000 is 1,100. You could be at 14,900. You might not be coming back to my IFR class. So you see, the problem with cold air is that you might not be able to clear obstructions that you think you should be able to clear. However, on landing at our destination airport, it's no problem because notice here, the quantity of error decreases to 0. And our separation from other airplanes is okay because they all have the same amount of error. They have the same kind of an error. We're a little closer to other airplanes, but not a problem. Okay, any questions on this? Okay, so you want to remember that if you're flying in colder than standard air, you're lower than you think you are. Let's take a look at page 67 in our yellow book. Page 67 in our yellow book. The FAA thinks you can't read an altimeter, so they're going to give you an altimeter to read. Now, the trick, let me tell you the trick. FAA says there's no trick questions on this test, but there is sort of a trick question here. They think that you don't know that an altimeter has 3 hands. They think that you don't know that, but an altimeter has 3 hands. You see here, look at here. This altimeter shows a pilot that's at 7,880 feet. See, the 1,000-foot hand shows him between 7 and 8,000, so he's not up to 8,000. The 100-foot hand shows him just approaching 900. So he's at 7,880 feet. There is a third hand here that's a tens of thousands of foot hand. Of course, this pilot's less than 10,000 feet. Now, if you look at all of these, which one of these shows the highest altitude? If you think C, you better look again. A, this pilot is 10,500 feet. See, the little hand is up beyond the 1. So this pilot's at 10,500. Over there on C, that pilot, he's not quite up to 10,000 yet. if the big hand goes around and comes up to the top, then it'll be at exactly 10,000. But A shows the highest. This is the trick on the test. If you know this, you'll get this right. Any question on this? Okay, I want to talk to you about, we're going to talk about true airspeed. But before we can talk about true airspeed, I need to talk to you about indicated and calibrated airspeed. Take a look up here. This is an airspeed correction table. This is what you find in your airplane flight manual. Take a look up here. I'd like you to notice that with flaps up, notice that when the plane is up at cruise speed, while it's indicating 100, it's really going about, its airspeed indicator is about correct. It's really going 100. As you get down to slower speeds, there's a mechanical error in the airspeed indicator itself. Let me explain it to you like this. When you're in cruise, the pitot tube is lined up with the airplane and it's scooping up all the molecules. But if you cut your speed in half, you fly with a higher nose attitude. So while your speed has been cut in half, not all of the air goes straight in the pitot tube. So we might actually be getting less than half of the molecules in the airspeed indicator. While our speed has been cut in half, our airspeed may show less than half. At slow speeds, there's a difference between what your speed of the plane reads and what the speed of the plane really is. So for instance, you notice at slow speed, there's 9 miles an hour of air in this airspeed correction table. When the pilot's indicating 60, he's really going 69. Have you ever noticed this? You might learn, your instructor tells you that the stall speed of your airplane is, for instance, 65. He tells you that the stall speed of the plane is 65. Haven't you wondered why it is that when you go out to practice stalls, he made you learn that stall speed was 65, but haven't you wondered why it is you seem to be able to fly slower than 65 and the plane doesn't stall? Have you ever wondered that? This is why. Because there's an error in the airspeed indicator at slow speeds. In other words, you can fly this plane all the way down to 60 and you're really going 69. You thought by all rights you should be stalled by better than 5 knots. But the fact is you're really going 69. You're really going, well in this case, 9 miles an hour faster than stall. 4 miles an hour faster than stall. But it looks like you should have been long stalled already. Right? That's because of an error in the airspeed indicator. All right. Now, so this is the difference between what's called indicated and calibrated airspeeds. So what is calibrated airspeed? I want you to know what calibrated airspeed is. Calibrated airspeed is indicated airspeed corrected for position error. That's our indicated airspeed corrected for maybe mechanical and position error, we should say. Sort of mechanical and position error. Okay. Now, I want to talk to you about true airspeed. Take a look up here. I want to talk to you about true airspeed. What is true airspeed? Well, true airspeed is calibrated airspeed corrected for pressure and temperature. Or you could just say true airspeed is calibrated airspeed corrected for density. Here's the idea. We have 2 airplanes here. 2 airplanes. One plane is down here at sea level. Another plane is straight on top of it, but he's up at 10,000 feet. Now, both of these are traveling at what we call a true airspeed of 100. True airspeed is 100. The guy at sea level, he's indicating 100. But the one up here at cruise, he's indicating maybe only 83. You see, the airspeed indicator has an error whenever you go up to altitude. Up here at 10,000 feet, these 2 planes are flying along in cruise, but the one at 10,000 is scooping up fewer molecules. So his airspeed shows slower, but he's really going just as fast as the guy below him. So true airspeed is our calibrated speed, such as 83, corrected for the density. You might say it's the calibrated speed corrected for altitude and temperature. Okay? Now, we can use our computer to calculate this error exactly. Before we use our computer, though, I want you to remember this. there is a ballpark correction factor of about 2% per thousand. So we're at 10,000 feet, that's a 20% correction. 20% of 83 is about 17. So about 2% per thousand is the correction factor. But it might be extra warm at 10,000 feet one day, so we can correct for that by using our computers. Let's get out your flight computers now, and we're going to do a correction for getting true airspeed. Take a look up here. Okay, what I want you to do is I want you to set up an altitude of 10,000 feet and a temperature of 0. Here's what you do. I want you to find on your computers a little window here, and the little window says on it 10. There's also a little thing, take a look up here, class, take a look up here. There's two windows, so I don't want you to get the wrong window. One of them says for altitude correction. That's for true altitude computations, and it's not even accurate. They don't ask you about it on the test anyway, so we're not going to use that in this course at all. But this one says, it probably says for true airspeed, it might say airspeed correction, it might even say for density altitude computation. Anyway, I want you to find 10 representing 10,000, and I want you to put that opposite 0, a temperature of 0. The reason I want that is that's the example I'm using, 10,000 and a temperature of 0. And when you locate that, I want you to find that. When you locate that, I want you to quickly show that to your neighbor. Exchange computers with your neighbor until both of you are sure you're doing that correct. Exchange that with your neighbor, and I'll walk around, and you guys can be sure you have that set correct. I'll walk around here. Okay, how y'all doing?
This one with this one, like that?
Yeah, exactly. Perfect. Perfect. Everybody doing all right here? Doing all right here? Okay. Looks good. Okay. If you got it right, you don't need to show it to me. Everybody looking good? Got that all right? Cassie, you got that all right? Okay. Looking good? Okay. Good. Okay. Good. All right. Everybody's looking very good. All right, class, take a look up here. If we have this set correctly, take a look up here, class. If we have this set correctly, here we are at 10,000 and temperature of 0. For a calibrated speed of 100, I'm going to show you that we'll be going a true airspeed of 117. Go to the inner scale here for the 10, representing 100. What used to be the minute scale is now going to be our calibrated airspeed table scale. Look at here. It even says on this computer, it says CAS on the inner scale for calibrated airspeed. For a calibrated speed of 100, look opposite that on the outside, and that tells you that your true airspeed will be 117. Look at the next one. For a calibrated speed of 140, find the 14 on the inner scale. Look opposite that, it tells you your true airspeed will be 164. Now, the last example here is stated backwards. That says if we have a true speed of 220, how fast will we have to go? Well, we'd have to have a calibrated speed of 188 in order to be going 220 true airspeed. Okay? Any questions on that? Everybody see how to do that? Okay? Now, what I want you to do is I want you, if you have any trouble with that at all, I want you to look at your neighbor and help your neighbor. Okay? If you all have that, any questions on that so far? Everybody not able to find that? Okay, now take a look up here, class. Just to be sure you understand what true airspeed really is, the concept is this. In the first example, I showed a pilot that's calibrated speed was 100. But he's really going 117 up at 10,000 feet. Now, take a look here, class. What I want you to know is this. What you might say, why is it important to know our true airspeed? Well, tell me this. Suppose that we have a way of, we figure our ground speed by noting how long it took us to go from one city to another city, all right, using ground speed checks along the ground. And we determine that our ground speed on this flight is 107. That's our ground speed, 107. What I want to know is do we have a headwind or a tailwind, and how much? Our ground speed is 107 on this flight. We figure that by watching the ground, by doing time distance, by watching checkpoints go by. Do we have a headwind or a tailwind?
10 mile an hour headwind.
We have a 10 mile an hour headwind. Because you see, we are really going 117 through the air, but our speed across the ground is only 107. Of course, our airspeed indicator shows 100, but that doesn't mean anything. We've got to correct that for the error of the pressure. See, so we're really going 117 through the air. So that means that on our return trip, we can figure we have a 10 knot or 10 mile an hour tailwind. See, so in this case, we have a headwind. The wind is blowing this way. We have a 10 knot headwind on this flight. See, our true airspeed is 117, but our ground speed is only 107. So we have a 10 knot headwind component. On our return trip, going the other direction, we can figure we'll have 10 knots on our tail. Okay. Any questions on that? Okay, now take a look up here. I've got another one for you that's just a little bit harder to set up. I used some super easy numbers a minute ago. I used 10,000 feet and a temperature of 0. Those were super easy numbers. But now we're going to look at some that are a little bit harder to set up. It's the same concept, but I want you to pretend that we're at an altitude of 2,500 feet with a temperature of plus 10 centigrade. And what I want to know again, I want you to set that up first thing. But before you set that up, take a look up here. Let me tell you, the FAA knows about the people that think that this 25 is 2,500 feet. That's 25,000 feet. Don't set that in there. Don't do that. The FAA knows about those people. 2,500 feet, that's way down here near sea level. So I want you to put 2,500 feet opposite plus 10 centigrade. And a tip, class, I have a tip for you. Take your pencil out. Mark where plus 10 is. Mark where 2,500 feet is. And line those two marks up right here. Put a pencil mark right here at where 2,500 feet is. Put a pencil mark where plus 10 centigrade is. Line those two up. If you line those two up, class, take a look up here. Take a look up here, class. If you line up those two, like I said, then for a calibrated speed of 120, you'll be traveling a true airspeed of 124. Why don't you set that up and then ask your neighbor to look at it to be sure you're doing it correct. I'll come around and help you. How you doing there?
I got it pretty good. The only thing I'm getting confused about is how do you know to go up to, how do I know to go to 120?
Well, because that's just the problem. The problem says you're going 120, okay? How are we all doing? Okay, you look like you're doing pretty good. See, you get plus 10 opposite 2,500? Let me use your pencil just a minute. Okay, now there's plus 10, right? Okay, and there's 2,500. So you're not quite lined up. Got it? Okay, you all see how to do that all right? You got it. Okay, any questions? Okay, class. Very good. Very good. Most of you know how to do that pretty well. So I just wanted to caution you, this is the old classic trick number 11, all right? And that is they give you 2,500 feet and have you set up 25,000 by mistake. Okay, I want to talk to you about the airspeed indicator now. I'd like you to turn to, see, I think this is 65, page 65, page 65. Let's look at the airspeed indicator. Take a look up here. Okay, class, I want you to become familiar with the arcs on the airspeed indicator. I'd like you to know that the white arc is called the flap operating range. That's called the flap operating range. The green arc, as it says right here, is called the normal operating range. The yellow arc is the caution range, and the red line, as it said, is the never exceed point. Let's talk about that white arc for a minute. The upper limit of the white arc is a structural limit. They don't want you to put the flaps down at a speed greater than the upper limit of the white arc because that can cause structural problems. The plane is not designed for that. It hasn't been flight tested with flaps beyond that because evidently they had some problems. So that's the fastest you can put the flaps down. The lower limit of the white arc is the stall speed with the flaps extended. Now the green arc, the lower limit of the green arc is the stall speed with the flaps retracted. Notice that as you would expect, the stall speed is lower with the flaps extended. Now I've got some good news for you, class. I want you to know that these speeds shown here are calibrated stall speeds. So what that means, of course, is that this is the calibrated speed it's supposed to stall at, not the indicated stall speed. So that means that these are markings on the side of safety, in other words. We might be able to fly the plane actually to an indicated speed a little lower than this, and the plane still flies. So these are sort of marked on here as calibrated speeds, which sort of means it's on the side of safety for you. So don't be surprised if you can actually fly the plane slower than the bottom of the white arc in a clean configuration and it doesn't stall, because these are calibrated stall speeds. Now I'd like to tell you that the upper limit of the green arc has a name. It's called the maximum structural cruising speed. I don't know why they call it that. But when you get into the yellow arc, that's an area where you're only supposed to be up there in very smooth air. When you get up to the red line, if you get past the red line, you might get all kinds of tail flutters. You might get a flutter that causes metal fatigue and causes a tail to break off. So you might think of this as never go beyond this. And sometimes you can go in here. And you can almost always go in the green arc. But I want you to think of this. If you're in the yellow and it becomes bumpy, that's as bad as being past the red in smooth air. A little bit of bumpiness can cause a flutter to possibly occur if you're in that yellow arc. Now, on your FAA test, they'll say to you, what is the maximum structural cruising speed? They always ask this question. And a lot of people miss it. You know what they put down? They put down this speed here as the maximum structural cruising speed. This is called the never exceed point. Don't get confused. The red line is the never exceed. This is called the maximum structural cruising speed. That's just the name of it. It doesn't have a whole lot of significance. Most planes, however, don't cruise up into the yellow, but there are some planes I've seen running regular, normal power. You can actually cruise them up into the yellow. So this isn't really the maximum speed the plane can cruise, but it's just called the maximum structural cruising speed. Okay. Normally, though, your plane will cruise down in the green arc area. Now, class, there's another airspeed that's not shown on the airspeed indicator. It's very important, and that speed is called the maneuvering speed. Don't bother looking this up in your manual. But in every flight manual, there's a speed shown in there called the maneuvering speed. This is sort of a rough airspeed that guarantees you structural integrity of the aircraft. If you're going at this speed or slower, it's supposed to be impossible to exceed the design load factor of the airplane. They're going to ask you on the test. They're going to show you an airspeed indicator like this, and they're going to say, what important airspeed is not marked on the airspeed indicator? And what's the answer, class? The maneuvering speed. Now let me tell you a little bit about how this maneuvering speed works. The idea is this. Now this isn't exactly correct, what I'm about to tell you, all right? It's not exactly correct, but the concept is correct. Take a look up here. If we have a plane that stalls at, say, for instance, 50, that's the stall speed of the plane, and if the plane has a designed load factor of 4 Gs, 4 Gs is the design load factor, we know that at maximum design load factor then, the stall speed of this plane is 100. What does that mean? That means that if you were going to go into a pull-up, a tremendous pull-up, you were in a dive and you were going to pull it up. If you were going to pull 6 Gs in that pull-up, that's a lot of Gs. If you were going to pull 6 Gs, now the plane's only stressed for 4 Gs. That's all it's stressed for. Beyond 4 Gs, the wings come unglued. You're going to go into a pull-up and you're going to pull 6 Gs in the pull-up. If you're going less than 100, it's impossible to pull 6 Gs. You can only pull 4 Gs. Because what happens if you're going less than 100 when you begin this big pull-up? The plane stalls. But what happens if you're going more than 100 when you're in this 6 G pull-up? And what happens whenever you exceed 4 Gs then in this pull-up? The wings fall off. So if you knew you were going to be in severe turbulence in a thunderstorm, all of a sudden you find yourself in a thunderstorm with severe turbulence, and you're afraid that the wings are going to come unglued in this, the best place to be is right around the maneuvering speed or below. What happens if you're 20 knots below the maneuvering speed? What happens then, though? You're running a greater risk of stall. What happens if you're 20 knots faster than maneuvering speed?
Starts with
You're running a risk of exceeding the design load factor of the airplane. So if you're in severe turbulence, or if you're going to be doing any acrobatics, it's always a good idea to be at maneuvering speed or less, because that guarantees you can't exceed the design load factor of the airplane, because the plane will stall first. Now the reason I say this is approximately correct is this: if you were to figure out the load factor for a plane and look at the maneuvering speed, it doesn't work out exactly correct. The reason for that is because the load factor actually has a 100%, 150% safety factor to it. Some additional safety factors in it. So it doesn't work out exactly right, but it's approximately correct and the concept is correct. Okay, take a look up here, class. I want to talk to you right now about the magnetic compass. They always ask about this on the test. Turn to page 67, please. Turn to page 67. I want to tell you about some errors in the magnetic compass. I want you to make a little picture that looks like this. It says something about acceleration error, and this says turning error. That's supposed to be an L there. That's A-C-C-E-L. Acceleration error, and the other one says turning error. I want you to make that picture right now. Okay, if we have that complete, let me show you what I want to talk about here. There's an error in the compass called acceleration error, and they're going to ask you about this on the test. Before we get started, let me tell you this. This is really what I want you to know, the main important thing to know. However, we must know more than this, but keep this in mind. The only time the magnetic compass is really accurate is in straight and level, unaccelerated flight. Anytime you turn, there's an error in the compass, and anytime the plane is accelerating or decelerating, there's an error in the compass. Now, here's the way acceleration error works. Take a look up here. Here we are in an airplane, and that airplane is headed straight west. If the plane accelerates, in other words, you put the nose down, making the plane dive, the airspeed is increasing. If the plane accelerates, the compass will show a turn towards the north, although you're really not turning. It would show a heading like this, although you're really not turning. If we put the nose of the airplane up in the air, causing the airspeed to decrease, making the plane decelerate, then the compass will show a turn towards the south, although the plane is really not turning. Now, this would also happen on east or west. If we're going east, the same thing. If you accelerate, it shows a turn towards the north. If you decelerate, it shows a turn towards the south. Now, there's a gauge for this. Take a look over here. The gauge for this is the word ANDS. A-N-D-S. And it means accelerate north, decelerate south. ANDS. Accelerate north, decelerate south. Okay, now let me tell you this. If you're going northwest, it does this, but only about half as much. If you're going north or south, it doesn't do it at all. There's no acceleration or deceleration on north or south. The greatest error is on east and west. Now, take a look up here. So far, so good. Everybody understand that? Now I want to talk to you about turning error. We're going to get in an airplane and we're going to put it into a bank, a shallow bank. Only about 15 degrees of bank or less. 10 degrees is better. Now, if you turn more than 15 degrees of bank, like maybe 20 degrees, the instrument sticks on the side of the casing and it's totally unpredictable. But assuming we're in about a 10, 15 degree of bank, and we let the plane sit there and turn. We just let it keep turning and turning all day long. There's nothing but turn. You'd notice this. Every time the heading of the aircraft went through east and west, the compass is about correct. But every time in our turn we go through north, we'd find the compass is lagging behind the plane by about 20 to 30 degrees. As you go through south, you'll find that the compass is leading the plane by about 20 to 30 degrees. So here we are, class. We're sitting here, we're making right turns all day long. As we get up to north, where's the compass going to be? It's going to be behind us. Now we can tell we're going north because we can look down at the section lines on the ground. Or we might look at the directional gyro. We're going north, but the magnetic compass shows maybe 20 to 30 degrees behind us. As we continue the turn, the lag decreases. What will the compass show as we go through east? It'll show correct. All right? It's correct as you go through east and west. Now as we continue the turn, as we get to south, what's the compass going to show as the airplane is actually going through south? What's the compass going to show? It's going to show ahead of us by about 20 to 30 degrees. When we get to west, what's the magnetic compass going to show? It's going to show correct. If you go left or right, exactly the same thing happens. The compass always lags as you go through north, and it leads as you go through south. Now, being consistent, which it is, take a look up here and I'll show you something else that happens. What if you're going north and you start to turn to the left? The compass says, I'm supposed to lag. So as you start to turn to the left, the compass jumps the other way so it can hurry up and start lagging. You turn to the right, the compass goes to the left so it can hurry up and get in position. Now as you continue the turn, it continues to stay behind you with a lag. Now, let's suppose we're going south. Still, being consistent, when we start to turn to the right, what do you think the compass is going to do when we start to turn to the right? Sure, the compass will turn in the same direction. It will jump ahead of us. Okay, any questions on that? Alrighty. This is Cheyenne. This is elevation 6,156 feet. We're coming into land here. Now you know that your airplane has a stall speed of 50, we'll say. Your airplane has a stall speed of 50. And I told you earlier that we like to come in at about 30% above stall. So that means we like to come in at about 65. Remember, the stall speed is 50. We come in 30% above stall, which means we come in at 65. Now, class, tell me this. Why don't we come in slower? Danger of stall. Why don't we come in faster? Float. You got it. Very good. We're coming into Cheyenne now, which is elevation 6,156 feet. What are you going to do with your indicated approach speed coming into Cheyenne? The same? Higher? Lower? What? The answer is the same. The reason it's the same is because your indicated stall speed is the same no matter what your altitude. But you might, in other words, the indicated stall speed might be 50. If it's 50, it's going to be the same at 10,000 feet. You might say, well, how can the indicated stall speed be the same at 10,000 feet? Isn't the air thinner? Isn't the air going over the wing thinner? That's true. The air going over the wing is thinner, but remember, the ram air going to the pitot tube is proportionately thinner. So therefore, the indicated stall speed is the same no matter what the altitude. So if that's true, then, whenever we go into Cheyenne, we're going to use the same indicated approach speed as always, because the stall speed, indicated stall speed, is the same. However, as I was talking about earlier in landing distance, whenever we land here, will our landing distance be greater than it would be at, say, for instance, a sea level airport? Sure it would be. The reason is because we're actually going a faster true air speed. We're going 2% per thousand faster. We're going about 12% faster. So when we touch down, everything seemed the same until we touch down. When you touch down, all of a sudden your wheels are spinning faster, and it takes more braking to get the airplane stopped. Okay? Any questions on that? I want to talk to you about weight and balance. Turn to page 69 in your supplemental data yellow book. And this is a manual for a Speedbird, whatever that is. And I'd like you to notice that this shows the fuel capacity of this plane to be 42 gallons. It shows the usable fuel to be 38 gallons. So what I want you to know here, class, is that this plane has, first of all, 4 gallons of unusable fuel. This is fuel that cannot be burned during normally anticipated flight attitudes. I want you to know how much fuel weighs. I want you to put down in your notes or put it down here or somewhere that fuel weighs 6 pounds per gallon. You'll need to know this. Fuel weighs 6 pounds per gallon. All right? this plane holds 8 quarts of oil. And I want you to know what oil weighs. Oil weighs 7.5 pounds per gallon. Of course, this plane has 2 gallons of oil, that's 8 quarts. So we had 15 pounds of oil in this airplane. Class, this plane has an empty weight of 1364 and a max allowable gross weight of 2,300 pounds. You need to know, what does that empty weight include? Let me tell you what that empty weight includes. The empty weight includes any unusable fuel. So if we wanted to know what this plane weighs with full tanks, we'd add to the empty weight the weight of 38 gallons of fuel, not the weight of 42 gallons, because we've been counting the unusable fuel twice then. So I want you to know the empty weight includes unusable fuel. Now, let me tell you this. The empty weight may or it may not include the oil. You have to check the sample problem and see what the manufacturer did on a sample problem to know whether the oil is included in the empty weight or not. I can tell you that some years ago, prior to about 1976, the oil was never included, almost never included in the empty weight of the airplane. But after that, all the manufacturers got together, decided that they were, to be consistent, they were going to include the oil in the empty weight. So I believe most of them, after 1976 or 76 and later, included the oil in the empty weight. But on your test, you'll have to look and see what the sample problem shows, whether the oil is or is not included in the empty weight. Tell me this, class. You buy an airplane from Cessna, and after you buy it, you have all kinds of optional equipment installed, like a DME radio and a transponder. Will that be included in the empty weight? The answer is yes. That is included in the empty weight, all right? Naturally, right? Yeah. It is included in the empty weight because, you see, you don't have this put in by Joe's Storm Door and Transponder Company, all right? This has to be put in by a FAA-approved, certified mechanic technician type, all right? And he knows that the empty weight has to include optional equipment. So he'll have a new weight and balance form. And the old weight and balance form will have written across it in big letters, superseded by form so-and-so. If you go out to fly an airplane right now and you look at the weight and balance data, you usually see about 6 weight and balance sheets stapled together. Because each time a piece of equipment is added or subtracted, they have to do a new weight and balance form. So the empty weight does include optional equipment. They're going to ask you that on the test. Now, this plane has a maximum allowable weight in the baggage compartment of 120 pounds. Why do you think they only allow 120 pounds in the baggage compartment? Center of gravity. Is that right? That's right, yeah. Some people think it's because of center of gravity, all right? But that's not true, okay? The fact is, it's a structural limit, all right? It's a structural limit. You might say to me, oh, your airworthiness, come on. You mean to tell me the floor can't withstand more than 120 pounds? No, I don't mean to tell you that at all. That floor, as a matter of fact, can withstand almost 4 times that amount. This plane is stressed for 3.8 Gs. So that means that floor is really stressed to withstand 3.8 times 120 pounds. But we can't put in more than that, because what happens if we make a bad landing, kind of a hard landing? That weight set's going to break right down through the floor, all right? You might say, well, surely it's a balance factor, isn't it? No, because some planes even have forward baggage lockers where you could put enough weight to offset any weight in the rear. We could bring the balance within limits. That'd be no problem. So you see, it's not a balance limitation. That 120-pound placard in the baggage compartment, that is a structural limitation. That's the reason for that. Okay, now I want to talk to you about how to do a real weight and balance. I want you to move ahead to page 76, all right? Let's move ahead to page 76. We'll be coming back to page 69 in a minute. But move ahead to page 76, please. Okay, now I have just a weight and balance problem here for training, just to see you know how to do this. Take a look up here. Here I have a sample airplane. Let's look at the manual. This is an owner's manual. This shows an airplane that has a maximum allowable weight of 5,100 pounds. All right? The empty weight of this plane is 3,450. But if we want to determine if we're within balance, we have to understand a concept of weights, arms, and moments. Let me explain this to you. The manual shows the position of the pilot seat to be 37 inches aft of a point called the datum. The second set of seats is located 71.7, and the last set of seats is 105 inches after the datum. Take a look over here, class. Here's an airplane I'm going to draw here. We have an imaginary point called the datum. Now, if we look up datum in a dictionary, it would tell us that a datum is a point of reference, a point of which to make measurements from. The manual says that the pilot seat is located 37 inches after this datum. There's where the pilot seat is. 37 actual inches like you measure with your ruler. It shows that the next set of seats is located 71.7. 71.7. And the last set of seats is, what is that, 105? Okay, that's located 105 inches after the datum. If we look at the manual on the other side there of the page, it shows that the fuel, usable fuel, is located at 35 inches after the datum. Here's our fuel tank right here, 35 inches. And then we have the baggage located at 63. That's in the engine nacelle locker area. And we have another baggage area that's located at 124. So here's one way back here at 124. And then we have one that was, what was that other one at 63? 63. Okay. 63 inches. This airplane evidently has twin engine airplanes, and around the engine nacelle area, it has baggage lockers. And there's baggage lockers there, 63 inches after the datum. Now, notice what it says is your CG limits on that manual. Your CG limits are 35 to 43.1. Right here it says this. Your CG limits are 35 to 43.1. These are the allowable limits, right here, from 35 to 43.1. From 35 to 43.1. That's where our center of gravity must fall in order to be legal. If the center of gravity falls after that, the plane would be unstable. If it falls forward of that, we would have problems possibly in landing the airplane. I'll talk more about those problems in just a bit. Take a look up here. Now, the present center of gravity of this plane is 36.5 inches after the datum. This is our present location. But here's the problem we have. We're going to load the plane up as you see here, and I want to know where is our new center of gravity after we load the plane. I want to know if we're within the allowable limits. That's what I want to know. Well, here's the way you do this. Take a look up here. There's a formula we use, and that formula says weight times arm equals moments. We know the weight of the plane is 3450. We know the present center of gravity, given right here, is 36.5 inches after the datum. So the weight times the arm is going to give us an academic number called moments. Now let me tell you what we're going to do, class. We're going to list all of the weights we're going to put on the plane, and we're going to list the center of gravity location of all these weights. And we're going to take the weights times the arm, and that gives us a number called a moment. For all of these, weight times arm equals moment. We're going to do that for each one of these items. When we get that all complete, we add up the whole weight and we add up all the moments. Now, how do we determine the arm? All you have to do is know that, well, if I got the weight and if I got the moment, the arm must be available by simply dividing the weight into the moment. Sure enough, if you divide the weight into the moment, we'll come up with a center of gravity of 43.88 inches after the datum. That is our new center of gravity. Take a look up here. This is our new center of gravity right here. 43.88 inches after the datum. Are we legal? No, we're not legal. We're too far aft. Now, with our basic formula of weight times arm equals moment, we know that the problem says here that the CG location is 43.8 inches after the datum. This is 0.78 inches after the aft limit. In order to bring the CG within limits, 100 pounds of baggage was transferred from the cabin baggage area to the engine nacelle baggage lockers. Determine the new CG. Well, here's our present weight. There's our present arm. There's our present moment. We're taking off 100 pounds at station 124. So a minus times a plus is a minus. We've just lost 12,400 moments. We've added 100 pounds at station 63. We've had a gain of 6,300 moments. So our weight is, of course, still the same. It's like taking something out of one pocket and putting it in the other. Our weight is still 5,100 pounds, but this is our new moment. Now, if we divide the weight into the moment, there's our new center of gravity. Are we now legal? Sure we are. Okay, now this is the basic concept of weight and balance here. you take whatever the weights are, you multiply them by the arms, and that gives you the moments. And as long as you divide the weight into the moments, that gives you an arm, and as long as that's within limits, we're legal. Any questions on that? Now let me tell you what happens if you're too far aft. If you're too far aft, the plane becomes longitudinally unstable. In other words, as you rotate the plane, it wants to go extra nose high. As you put the nose down, it wants to overcorrect going down. It's hard to control the plane. It's what we call longitudinally unstable. Okay, now, if the plane is loaded too far forward, if the center of gravity is too far forward, what happens is you're using too much elevator to hold the nose up, see? So what you have to do, whenever the plane is real nose heavy, when you come in on a landing, whenever you come in, especially if you're coming in slow, you're using a lot of elevator to hold the nose up, and if you hit one of those sinkers, and you've got to flare the plane out, you'll find, oh, I've run out of elevator, and you hit real hard. See? You run out of elevator. Also, the plane has poor performance because when you're flying along, you're using so much back elevator to hold the nose up all the time. It has poor performance. So if the plane is if the CG is too far forward, we have big problems on landing. Okay, now, take a look up here, class. We're now going to turn to page 74. And we're going to do a weight and balance for a high-performance airplane that's a real airplane, like the kind you're going to have on your FAA test. Look at page 74. Now, class, this is a layout for an airplane. It's the sample that's given here of an airplane that has a center of gravity, has a pilot seat located 85 inches after the datum. Next set of seats 121, baggage area 140 inches after the datum. And we got two fuel tanks, a main tank and an aux tank. The only thing is, this plane has a center of gravity that's allowable limit changes as the weight of the plane changes. At max allowable weight, the center of gravity limit, as you can see here, is rather narrow, 82.1 to 84.7. At a little lighter weight, the center of gravity is much wider. So if our plane happens to weigh something in between there, it's difficult to determine if we're within limits or not. Well, take a look up here. Here's what you're going to be given on the test. This is all you're going to be given, is this page right here. Well, one other page. I'll show you that in a minute. This plane has an empty weight of 2,015 pounds. Now, the moments for this airplane are 1554, except this is /100, which means this number is really, you add 2 zeros to that, really. That's what you should do. All right? We'll talk about that in a minute. They're trying to deal with small numbers here. But the weight of the plane is 2015. The moments are 1554 with 2 zeros on the end, really. All right? Take a look up here. The front seat occupants have an arm of 85 inches. Circle at 85 right now, please. Circle at 85. Okay, the rear seat passengers have an arm of 121 inches after the datum. Circle that number. The main tanks have an arm of 75 inches. Notice that the aux tanks have an arm of 94 inches. Notice that the baggage has an arm of 140 inches. Circle all those arms. Okay? Now, take a look up here. Take a look up here. Everybody look up here. When we do a problem, when they give you a problem on a test, they're going to give you all these weights. All you really have to do is take all the weights and list them. You could just multiply them by whatever the arm is, except, take a look up here. I want you to circle this whole column of weights here. Circle that whole column of weights. Circle the whole column of weights. Now I want you to circle the whole column of moments /100 at the end. Circle those. These are the only ones that are important to you now, and I'll show you why. You'll list all the weights, and then we're going to list the moments, but we're going to figure the moments by taking, of course, the weight times the arm. That gives us a moment, but you got to knock 2 zeros off it. It'll give us moments /100. Now, take a look up here. You might say, why are we doing all this? Here's why. On the next page, turn over to the next page, we have a list of pre-divided numbers that will fall within the allowable limits. You see, our moments there came out to be 2390. All right, that was our moments, 2390. And if you look here, for a max weight of 2950, is 2390 within limits on allowable moments here? This is on the next page there. Okay? Are we within limits? These are pre-divided numbers that will put us within limits. Okay, look at here. Look at here, class. Take a look up here. Everybody look up here. Look up here. For a weight of 2950, we're allowed to have a minimum number of moments of 2422 to a maximum number of moments of 2499. These are our allowable minimum and maximum moments. As long as our moments are within that, we know that if we divide the weight into those moments, the center of gravity will be within the allowable limits. Okay? Now, take a look here again, class. Let's look at this again. Take a look up here. Take a look up here, class. Everybody look up here. Let me explain this again, make this clear to you. Let's run through a sample problem. They tell you that you have front seat. First of all, we have an empty weight of 2015. We don't even need this arm number here. I just put that in there for training. All we need is the moments slash 100. The moments of the plane, 1554, that was given to us over here. Here's where the moments were given, 1554. So far we've written down the weight and the moments of the airplane. Now, take a look up here. Take a look here, class. The front seat passenger weighs 415 pounds. You can see here that the arm of that passenger is 85. All we have to do is take 415, the weight, times the arm, which is 85, the weight times the arm, and that'll give us a moment. If you take the weight times the arm, the 415 times the arm of 85, you'll come up with 35275. But you've got to round that off and knock off 2 zeros and call that 353. Any question on that? You see how we did that? These are moments slash 100 here, and that's all that counts on this last graph to decide whether we're within limits or not. Now, you might say, well, why did they give us this whole chart here? What's the purpose of this? This chart is supposed to make life easier for you, but it actually makes this particular problem more confusing. Take a look up here. If you had 2 passengers and one of them weighed 200, you could just simply say, well, he's got a moment of 170. But the fact is, we've got 415 pounds of passengers. It would be nice if they had numbers for 415, but they don't. You can't even take 2 200s and then a 15 because there's no number for 15. Your best bet is just to take the weight of 415 times the arm of 85. And when we do that, we just simply take that 415 times the arm of 85. There's the moment, but now we've got to knock off 2 zeros and call that 353 moments. Now we do the same thing for the rear passenger. He weighs 110 pounds. 110 pounds times an arm of 121. There's 110 times an arm of 121 gives us 13,310 moments. And so on. We do that for each of these weights times the respective arm gives us the moment. Now, if you want to, take a look up here, you could do this. You could divide the weight into this big moment and come up with the center of gravity and maybe decide if you were within limits, but you see, because if the weight is a little bit off, if it's not exactly the maximum weight, we don't have the numbers shown. We don't know what are the allowable limits at 2,800 pounds, for instance. So because of this sliding scale for the center of gravity allowable limit, that's why they use this list at the end here on the next page, page 75, list of pre-divided acceptable moments. How many moments did we have in the one we just added up?
2390.
2390. Are we within limits on this chart? No, we're not. We're out of limits. We're out of limits. 2390, we're less than the allowable. We're not legal. We can't fly. We're too far forward.